All right, so today we'll get going on stuff. Hopefully this all works and I remember how to work everything, because I do this differently. I'm recording the, syncing the slides to the audio as well. So let's hope. It looks like it's recording. So let's see. Okay, so the stuff we're going to talk about today and next time is called Exploratory Data Analysis. And all it is really is making charts and graphs. It's a way to look at your data so you can get a feel for it. This is not stuff you would ever or hardly ever use to present in a paper or a conference or anything like that. This is so you understand your data. Because if you are going to explain your data to other people, you're going to analyze it, you at some point, at first at least, you have to be able to explain it, understand it yourself. Right? So you're going to find anything over the data set, you have to understand the data yourself before anybody else does. For your numbers. It's going to be easier then to find mistakes that you've made. You can make coding errors, right? So a lot of times it doesn't really matter if you're doing some sort of biological stuff or you're doing where you're coding behavior. You're watching, say, a tape or a video of an animal doing something, and you code you say, a 1 is this, a 2 is this, etc. Or if you're putting things in from a survey. Sometimes you make mistakes. It's bound to happen. You can also have software that does this, and the software is written poorly. That happens too. So you could find a mistake. An old friend of mine back when I was in grad school was trying to develop a system for that medical doctors could use to figure out very quickly how many cigarettes people smoke per day. There is a very easy way to do it. What you do is you take a saliva sample. Okay. Problem with that is not everybody wants to skid into it. They get sent off to a lab, and it's not invasive, but some people might think of it that way. What if you could find a way to ask people, say, 4 questions, and you could get a very good estimate of how many cigarettes they smoke today? That'd be great. So what he did is he had a whole bunch of questions, 23 different questions. One of them did include, how many cigarettes do you smoke a day? Okay, that was one of the questions. But it also had, and the people did spit into a test to the amount of nicotine in their saliva and the amount of cotinine, which is a stable metabolite, and they know the half-life of it. So you can get a really good estimate that way. But also questions like how much time before your first cigarette in the morning? Have you tried to quit before, yes or no? Could you quit today, yes or no? Things like that. And one of the things when he was looking at the data, and he did it at the Ontario Science Centre in Toronto, it's a great place to collect behavioral data because people are interested in science. So you set up a little table and you say, could you fill out this consent form, fill out this questionnaire? People do it because they're in science, so it's a great population to study. So he had people do this, and one of the records in the data set had 500 records, and the person said they smoked 400 cigarettes a day. That can't be true. Like, that's professional level. You screw the Olympics, you go pro, that is amazing smoking level. But you can't smoke that much. There's what? There's 25 in a pack, a large pack, right? So that's, let's see, so that's 16 packs a day. You can't smoke that much. You probably could for a day, and you'd die of something.
How much nicotine can you?
Yeah, I mean, it would be amazing. You probably can't do it. So he must have made a coding error. Now, he doesn't know what the coding error was. It was probably 40. 40 is a pack and a half a day. That's a not unlikely level of cigarette smoke. It's a lot of cigarettes, but this was 1987 when they were $2 a pack. So there's a mistake there. And he found it by doing this, by just looking at the data, making scatter plots, charts, graphs. It's easy to guess what actually happened in an experiment. If you make look at all the stuff on the blackboard. If you make just a quick bar graph of something and you've got a couple of groups, it doesn't matter what the hell, we're not going to worry about what the thing is we're studying here, but if I make a bar graph and I see this, I think I know something happened. And do I know it's significantly different? No. But there's a difference between group 1, group 2, and group 3. And if I look at that and say, I predicted, when I designed this experiment, I wanted group 1 to be the lowest, group 2 to be highest, and group 3 to be in the middle, I can look at that and say, probably reasonably, yes, my experiment probably worked. It's not a ridiculous thing. I have to go through it now and analyze it, but I can at least look at that and say, good, something good happened here. If something was really different than that, and this is what I expect, I might go, oh, geez, what the hell's going on? I have to look more closely at this. It's also easy to find odd values, what are called outliers. Going back to my friend, I should say ex-friend, because he's not a good person, had to resign from his job for sexual harassment this year. This guy. Just saying. Weird. Seeing that in the paper. I knew what university he was at. And he was a psychologist. And I saw this thing come across my Facebook feed, and I went, oh, please don't be. Please don't be. Please don't be. Oh, no. Retired early. Wow. Anyway. Odd values. Like in those data, one of the questions asked was, how old were you when you started smoking? Sorry, I have to keep checking this. My wife took my keys and I have her keys. I'm here, teacher. Happily, we share my office, so I have an office key and a house key, and there's a car key on my key, so it all worked out. But if she pushes the little tile thing, my phone will ring. I love all that stuff, by the way. I love talking to my house and it does things. Alexa, turn on the dining room. It's I feel like I'm in the future. So one of the people in their thing said that they started smoking at 4. That's probably not true. Yes, I know it happens. Yes, we've all seen the videos on there's some weird video on YouTube of some kid smoking and he's like 3. It's like, hey, you shouldn't put that on YouTube. That's just saying I'm a bad parent. That's like an invitation. Please take my children. I'm unfit. Right. So, but that's an odd thing, and you might say, well, do you want to remove that? Is it a coding error? I don't know, because if it's a coding error, I don't know what the number should be, and frankly, that's a different population of people than normal people. Typically, people don't start smoking at 4. It was probably 14. It could have been 24. Probably wasn't 4. You probably want to remove that. So you can do this kind of thing. It's an important thing to do because it'll allow you to find these mistakes, in essence, that you've made. Okay. So what this is all called, as I said, is exploratory data analysis. It's probably the most ignored part of statistics, and it's probably, I shouldn't say probably, I'm not really sure about that, but it is a really important step that a lot of people skip. These ideas were put together, they weren't really developed, I shouldn't say that, but the idea of doing this was championed by John Tukey. You may have heard of Tukey, you may have, he's a statistician, of course I know you all have a favorite statistician. And it allows you to generate hypotheses from data and also just to get a feel for your numbers. When you are looking at data that you collected, especially if you've got a big data set, you want to know what happened so you can figure out what kind of tests to do. My PhD advisor used to always say, statistics are there to prove what you already know. You already know it because you did the experiment. But it's to prove to yourself and other people that this isn't just random chance, that this actually happened, and I can show you the likelihood that it's just random chance. And you don't lose any richness in the data when you do this stuff. Basically, this is a way so you can look at something and you can say, I can reconstruct a data set, but I can look at this as a picture. Okay? So I don't know what these numbers are. Let's pretend they are, oh, they're scores on a test out of 35. Let's go with that. How many people do we have in the class? 1 and 2 is 3, and 5 is 8, 10, 11, 12, small class. We look at that, we say, let's see. We can just look at this and see that most people got 25. 25 out of 35 is not bad. Right? It's what, 71? I think so. 5 seconds. That's okay. I'd be happy with that. Somebody got 33. Person got perfect. Somebody didn't come to class. Or maybe came to the wrong class and wrote the test because they were embarrassed. I think I did. Those of you who took brain behavior, I told you the story of me going to a 4th year chemistry class by mistake in 1st year and just sitting through it because I was so embarrassed. This isn't history. So just something like this, even though it's a very small data set, this groups stuff so we can get a feel for it. So those kind of frequency tables, they make a lot of stuff easy. Like we can get, let's say we want the sum of all the scores. We probably use that to maybe calculate the mean. So we can just do that very easily by doing the sum of the x values, that's the scores times the frequencies. I know this has an exclamation point probably in the slides if you have them. I fixed that for you. Or a 0 or something, like I didn't, I didn't shift the thing. And every year I said to myself, I'm going to fix that. And I finally did. So it's 309. I don't know if that tells us anything, but if it's 309 divided by 12, we can get the mean pretty easily. Right? Now, one of the things you can do that's a little more, now we're getting a little more graphy, if that's a word, is we can do a relative frequency histogram. And all this is, now you know how I made this? I didn't use Excel this time because I'm using Keynote. It plays well with numbers, the Mac program. So I put the numbers into Keynote and I just said histogram. I didn't give it any parameters. I said just make me one. Because again, I'm not using this for any other purpose than for my own, just for looking at something. So it's not pretty. It's not meant to be pretty. And yeah, the axis doesn't make a lot of sense in a lot of respects because it's labeled 1.25. Well, if these are individual people, a quarter of a person doesn't mean anything. That's not what this is for. This is so I can look at the numbers and get a feel for them. Right? So there's a histogram function in almost any spreadsheet program. In any spreadsheet program, it's worth it. There are histogram functions in any stats package you use. I've lost no richness in the data. I can literally go through this and figure out what each number was very easily. I can say I've got, even though I can go with one person who got, looks like that's 10, 35, 33, right? We've got 2 people who got 29. We got, looks like 5 people got 25. Oh yeah, okay, I can redo that. I can totally rebuild it. That's nice. It's very useful. Batteries are dying in my mouse here. Oh well. Do it the old-fashioned way there. So I can reconstruct the data set if I have to. I used to have weekly data meetings with my PhD advisor. And because collecting animal data takes a long time, it's not like some surveys, fill them out. So the experiment goes on for months, and every week I would come in and I would bring not the raw data, that's of no use at all, but I'd make a graph. And we could look at it and we could say, oh, this is what's happening. Oh, there's last week's graph, there's this week's graph. Things like this, very, very common. Really nice way for me to get a feel for my numbers and for my advisor to get a feel for them. I can spot an oddity. This is weird. There's something odd. Again, let's pretend it's tests. This would concern me if this was my class. I would look at this and go, ooh, somebody's not doing this so well. And in fact, I do this after I give tests. I quickly have the spreadsheet program make me a relative frequency history. And it just does that so I can look at it and go, okay, good. Because it calculates the mean for me all the time, the standard deviation, because I like to know that. But I also want to just look at, is there something weird going on? And oftentimes in a bigger class, I expect something like that. A couple of ones that aren't so good, because some people don't come to class. Some people are registered in the wrong course. By that I mean they shouldn't be in the class because they just aren't going to do very well. It happens, right? So when I was teaching intro psych, and after the first test, which is, let's say, out of 40 multiple choice questions, there would be people who got around 10. And I look at it and think, there's only 4 alternatives. That's random chance. There are people in here that are doing as well as a monkey would do. That's a problem. Let's find out who these people are and see what the issue is. Right? Or you see a whole bunch of people that have exactly the same mark, and you go, that's interesting and unlikely. I wonder what that means. And sometimes you get an email from a student after class saying, 3 people cheated. I saw them. And then you fake in the class, this is fine in this one, intro psych. I got an email. There were people cheating in front of me. I said, thanks for letting me know. You don't know their names, and there's nothing I can do about it. Next class I came in and I said, I know some people cheat that. Because there's cameras in the room and I hacked into them. Like, people believe anything when they're in first year. You think I'm sitting up here on my computer just watching movies? Yes. That's what I was doing. And if you come up after class and admit you cheated, I will not have you expelled. But you'll get 0. But if you don't, I will, because I know who you are. 5 people. It's the thing I can do once in my career, but I'm so proud of it that I tell the story all the time. It's a great moment. It was a great moment. It was like 2005. It was in that room over there, the lecture room. And because I have this reputation of being sort of into technology, people just believe that I can hack into security cameras, which aren't even in there. It was a great thing. All right. Now, those are frequencies. With categorical data, it's a little bit different. You get a bar graph. It's got a different name. Doesn't really matter. I'm never going to ask you what's the difference between a bar graph and a histogram. If you don't know that yet, you probably shouldn't be in here. A pie chart. I don't like pie charts. They don't do anything for me. I think they're a poor way to present data. But if you're doing it for yourself and you like a pie chart, that's what you should do. They're easy to do. Again, you just select something and go from there. The x-axis doesn't have a scale. That's the big difference with a histogram, right? So the x-axis has no scale, whereas in a bar graph with a histogram, of course, it has a scale. So let's say it's stat 2126, right? Which is where I originally made the slide for, which is probably, we have seen this slide, I think Dwayne has it. And we used to have, people see guys, we used to take stats. And we got some biology people, sociology. So that's what I used to take. This is maybe a snapshot of like maybe 8 years ago in that course. So, what does this mean? It just tells me nothing, or other than most of the people in that class are psych students. Along here, the x-axis means nothing. Right? How far away it is from the origin doesn't mean anything. Right, so it's not that this is one better than this. That's stupid. Categorical data are weird. You got to be kind of careful with them because sometimes categorical data have numbers attached to them, but they mean nothing. Right? TV channels have numbers. Right? But channel 3 isn't one better than channel 2. Channel 3 is global, channel 2 is the weather network. I don't know. Global's better than the weather network, probably, except for weather. Is channel 4 twice the channel 2 is? No, it doesn't mean anything. Right? But as long as you understand that, that's fine. So here's the pie chart. You see, that does nothing for me. If that does something for you, that's great. But people do this, and again, you wouldn't really do this to present anything to a group. This is just to do this for yourself. It doesn't do anything for me. This makes a lot more sense to me. I think if you're in like Probably business, they use a lot of pie charts. I get the feeling they do. I don't know if that's true or not, but I think they say things like, here's the projections for the sales for the first quarter. And and they just say that. Here's a little something our art department's come up with. Here's the marketing projections. And they just say words. We have to liaise with various stakeholders. I love that, by the way, the fake talking people do. Oh man. I was in a meeting with someone today. We had to liaise with stakeholders. Says, "Do you want to talk to people?" Is that it? I literally once had a colleague say, "Can you repeat that in English, please?" Which was a great moment. So that's useful. I don't know that it's. This is again stuff you know how to do. So with quantitative things, again, as noted, we use a histogram. It's a bit different. One of the nice things here with quantitative variables, you can see a central tendency. It's kind of hard to do that with categorical variables. We could see that the most common major there was psychology, but it isn't really, it's not the average really, right? Whereas with quantitative variables, which I prefer, I like things that I can say one is better than another, and I can assign a number to it. Scientists are supposed to quantify things. Not much on qualitative things. Sometimes you have to, but. So we can see the central tendency, which is an important thing. We can see how spread out something is. And we can see the shape. And in fact, those characteristics, the central tendency, the spread, and the shape, are really the way you describe any set of data. Right? That's how you describe data. Like if I said to you that we have a normal distribution, like a bell-shaped distribution, the mean was 65, and the standard deviation was 10, you can get a pretty good picture in your head of what it looks like. If I tell you we have a bimodal distribution, you know what that looks like. That looks like PSYC. So these are my wife's cases. You can see they've got all kinds of fun things, all little girly things attached to them. It's like USB key is a girly thing. This, I don't know what that is.
USB things can be pretty.
Lots of stuff.
Is yours Wonder Woman? This is my USB, Dave.
What is it? Oh, that's great.
Mm-hmm. Yeah, mine's a hot song.
Yeah, no, Mr. Smart. It's only 2 gigs though. So
This one's, I think, 16.
ah, very nice. Okay, here's something we can talk about shape. We can talk about how skewed something is. So if we have a negative skew, it means it's shifted over to the right and there's an elongated tail at the left, positive skew. And I know, does anybody else find that completely ass backwards?
Yes.
Okay, because I do, I always have, but it's actually correct. it seems backwards, doesn't it? But here's the mnemonic. The tail tells the tale. Huh? Pretty good, right? I didn't invent it. I feel silly saying it. But when you say something skewed, negatively skewed, it actually means that most of the data are over to the right. This is the kind of distribution I expect in a class like this. This is what I typically get. Very few people do poorly in a class like this. Anything that's required for people to do an honors degree typically is all mostly over here. That's the way it works. This is one of those things I don't tend to talk about it a lot. Skewness, you can. There are ways to measure this, right? So when you look at statistics for a distribution, there are measures of skewness. I don't know how they work. I assume if I ever need to, I can look it up and read about it. I don't know how they work. I believe there's a formula. That's all I got. We can talk about kurtosis, which sounds like a procedure. It sounds like something they can do outpatient nowadays. Got a bad case of kurtosis. So, leptokurtic means it's peaked. Platokurtic means it's flat. So you would say, I am more leptokurtic and Paul is more platokurtic. Thank you. It's a fact joke. We do that to each other all the time. You guys understand that, right? He makes wine jokes about me, right? I know that, so it's okay. I would say that, say, Brandon Champ is more leptokurtic than I am. I never remember these terms. So I'm never going to test you on them. I'm saying that again, you can get a measure of kurtosis, and it doesn't mean a whole lot to me. What means a lot to me is I can look at, see how peaked a data set is, and it tells me something. Right, so if they're all peaked together like that, it's telling me that there's not a whole lot of variation. If it's spread out more, that tells me that there's more variation. But these all have the same mean of 0, as you can see here, but they're more or less spread out. Okay. Questions so far? This is all stuff you probably know. You may not know these terms, may have ran into them. Doesn't matter. They're not horribly important terms. Okay. So a distribution is symmetrical or asymmetrical. It can also be unimodal, bimodal. I guess it could be trimodal. I've never heard of that, but I guess it happens. Right? Many variables are unimodal. In science, there's a lot of bimodal things too. There's one way or another kind of thing to do things. It could be a uniform distribution. This does happen. So you can get a uniform distribution where every possible value is equally likely. So every value is equally likely. That's a uniform distribution. That's about the 3 most common things you're going to run into. Yeah, these batteries are dead. Oh, should have checked that. We've got a connection again. We'll see what happens. Here's an example of actual data. Mario Lemieux was an amazing hockey player, or as he was called in Pittsburgh in English Canada, Mario Lemieux. That bugs me. There he is in the 2002 Olympics when we won the gold medal for the first time since 1956. Here's some goal totals from his career. 43, he was 18. 43, 48, 54, 70, 85. That's a lot of goals to score in a season. Even if you don't follow hockey, the benchmark, the big thing is 50. People get really excited about 50. 19. He had a lot of, just take a look at this. You can actually get a feel for his career if you know nothing about hockey. Okay? There are 82 games in an NHL season. Okay? If you know that, and you can see that this guy obviously scores a lot, then he has some weird years. What happened here? Wow. He probably had some injury problems in his career. Look at that, 19. 17. It's not that he was great and then shitty, then great, probably. It seems unlikely, doesn't it? It's probably that he got hurt. He had a tendency at a back problem for years. Right? So he had a back problem, and he would get hurt, and he wouldn't be able to play for long periods of time. He then retired here. then he bought the team. Well, they owed him so much money in pay, and they couldn't pay him, so he said, I'll just take the team then. And then he didn't play for like 4 years, and then he decided he wanted to play again. So they unretired his number, which was one of the neatest things. His son was standing there at center ice, and they took the banner down and gave it to his kid. Really cool. And then he played that game and got 2 assists. Like, yeah, I'm back. And the weird thing was, he wasn't the captain of the team, or, you know, and there's the coach. And like, you could see him looking at the coach like, you know, I could fire you. Oh, he also, which year is it? This year, he won the scoring title for the whole league. He scored 44 goals. He only played 60 games because he was out for 20 games with cancer. He was off for 6 weeks because he had non-Hodgkin's lymphoma. Oh, I'm better now. Take me off the disabled list. I don't have cancer anymore. And he won the scoring title. Like, he was an amazing hockey player. If he wasn't hurt so much, we'd probably consider him the biggest hockey player of all time at Wayne Gretzky. So I chose these data because there's all these interesting, weird things that happened because he had these injury problems throughout his career. Oh, when asked why he got better this year, he said, I quit smoking. I love hockey. So a histogram may be useful, but you might want to group the values somehow. So what I've done here is, again, I just said make the histogram. I put the numbers in, and I asked numbers, the program called numbers on the back, to make me histogram. And it made me. These are just these midpoints here. So in fact, you might wonder, he never scored a 90. Yeah, but 85 to 95. 84.5 to 94.5. That's what I think years for 85 goals. That actually fits there. You can see usually he hits the benchmark of superstar NHL player, and then he's got all these weird years where he's hurt or has cancer. I had him in a hockey pool that year. And I said, I'm not going to drop him from my team. I bet he comes back. He's superhuman. And he did. Right? The worst thing was, another buddy of mine had 2 of his line mates. So every time, when he came back, the other, my friend, got every time Mario scored, you know, his team was a Mark Recchi, also got points. So that's kind of useful. So that's 85 to 94, or 84.5 to 94.5 is what it is. Okay? You probably dealt with all that stuff in the intro stats, real limits and all that stuff. Look, don't worry too much about it. The point is, it's just you got to have a half, so it's 84.5 to 94.5. Yeah. 84.5 to 85.5. All right. So that's useful. We have to make sure that the scale makes sense. Especially the y-axis. You know, you hear people say that it's easy to lie with statistics and you can have statistics telling you anything you want. In some respects, that is true, but that's if it's done improperly. So, I remember, in fact, when I lived in Newfoundland, there are really 2 ways to heat your house in Newfoundland. There's electricity and oil. Okay? It's funny, there's natural gas that's they have there, but it's all pumped to the mainland and sold. No one has gas heat. Some people have propane. You have a propane tank inside your house, so you have a giant burner. Or you have a giant oil tank inside your house, and a truck comes and fills your house with oil. Not your house. That would be weird. Fills the tank with oil. Okay, so why am I telling you this? Because there was this push, because electricity, heating your house with electricity, unless you do it properly and are careful, it can be expensive. It's like just burn a pile of 20s for heat. So the electrical company was trying to get people to switch from oil to electric. And they had a little mailer out to people, and in fact, the graph looked a lot like what we have here, but it only has 2. But it only had 2. Things here. electricity is more reliable. It's maybe a little bit more expensive, but it's more reliable. And that's true. When you run out of oil, that's a problem. And that could happen. Unless you check the gauge on your oil tank and go, oh, we better get some more oil. So you can run out of oil, and that's that. Electricity is more reliable, but it's more expensive. So this mailer thing looked like that. Dollars. Except the scale of this thing was so small that it made it look like it was nothing, but it was like $100 more a month. It was this beautiful, almost a textbook example of lying with a graph. So if you make this go, per month, 100, 200, 300, whatever. But all these gradations were like $50. Well, that's $100 a month. It doesn't look like a lot, and it wasn't a lie. It was just poorly graphed, poorly presented for a reason, data. We have a federal election coming up this year. You'll see that done by all three major political parties. They all do it. They all do it. Some more than others, I will say that. But they all do that stuff. So make sure your y-axis makes sense. And it did with our Mario Lemieux example, so we're okay. You have lost, when you do the grouped histogram, you've lost some of the richness in your data. So that wasn't a big data set we had, but if we had a really big data set, we might not want to lose the richness in the data, but we still want to get the shape. So there's a couple of things you can do here. And the classic sort of approach here is what's called a stem and leaf plot. This is technically called an ordered stem and leaf plot, because I've got them in order, right? So it goes like 1, 6, 7, 17, 19, 28, 35, 43, 44, 45, 48. You can do it with an unordered one. I don't know why you would do that. I think that comes from the time before people did this with computers, and what they would do is they'd do it by hand, and they just would read them, right? So you'd say all the 50s go here, all the 60s go here. But you typically would order it. The nice thing about this is I've got roughly the same thing I had before with the histogram, except I've got the actual numbers in it. You would never put this in a paper. You would never put this on a slide for a talk. But for your own edification, you can totally do this with your own data. Because it allows you to spot something. Or some things. So, like I said, it's an ordered stem and leaf plot. There are unordered ones, which is bizarre. So you interpret this the same way you would interpret a histogram, right? Just look at, you can get shape from it. And it's easy to spot outliers. I don't know that we call these years outliers. There's enough of them that to call it that. Probably not. But it allows you to see that there are sort of two different Marios. There's this guy here who's hurt, and this guy here who's not hurt. You can see that right away. Preserves all the data. We have all the numbers here. It's totally possible to get every single number. It's easiest to get the middle, or the 50th percentile. In this case, it's 44. How do I do that? Well, how many numbers do we have? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 13, 14, 15, 16, 17. So let's see, that'd be 8 on one side, 8 on the other, right? The middle number is going to be 1, 2, 3, 4, 5, 6, 7, 8. Oh, there it is right there. It's 44. That was easy. You just have to be able to count. You have to have a formula, you have to be able to count. Nothing complicated. It's dead easy to do. All right, questions so far? I know you probably know all this stuff, but okay. No, that all came up at once. This also allows us to get something called the 5-number summary. The median is one of those numbers. That's the 50% of the median in the middle. We can get the first and third quartiles. The first quartile, that's the 25th percentile. That's halfway between nothing, the first number, and the middle number. Okay? And that's going to be 18 in our case, and 61 and a half. And how did you get that? Well, because I'm going between two numbers, I'm doing what's called basically linear interpolation. What's the number that will be right between those two numbers? Okay? So now I've got the minimum, the maximum, the first quartile, the third quartile, and the median. So the first quartile, the third quartile, the median, the minimum, the max. And those things give us, that's what's called a 5-number summary. Okay. I don't know why they keep coming up all at once now. Oh well. Well, I guess because I didn't order them, whatever. Yeah, so the minimum and the maximum. That gives you the range. That's now we have a very crude measure of spread emptiness, right? It's the range. You could call it 84, 85 minus 1, or you could say 1 to 85. Either one's fine. Because again, typically you're not going to use the range as something you report in a paper. You would use it for yourself. It's for you that you do this. And you take these things, you can make what's called a box plot. Or it's sometimes called a box and whisker plot, which sounds like it was made for small children to make them interested. Oh, it's a box and whisker plot. It's fun. It's a box and whisker plot. It'd be like a horrible cartoon series made in the Soviet Union about statistics. Box and whisker. That's the strangest thing perhaps I've ever said. There's a long list, man. There's a lot of competition there. Okay. I made one of these for this. In SPSS, there's an option where you do what are called descriptive statistics. You just click and you click box plot, and it gives you a box plot. In Excel, it's virtually impossible. You have to go through 83 YouTube videos to figure out how to do it. Or you can just draw it yourself. Get a piece of graph paper, which is it's this old-timey stuff with little squares, and you just draw it. It's easy. Again, you're doing this for yourself. I have seen box plots presented on slides. This is the first of these techniques I've actually seen where someone said, here's some of my data. Because look what this gives us. This is the minimum, the maximum, the first quartile, the third quartile, and the median. This tells us there's a lot more numbers bunched here because there's just as many numbers in between the median and the third quartile as there is between the first quartile and the median. So that tells us we've got a lot more numbers here. It tells us something. It's not, again, this. I guess I've seen it. I was really surprised. In fact, I was at a conference of comparative cognition in Florida. This was probably 2 years ago. And someone put up box plots to show their data. Wait, it was very useful. And I actually got 2 texts during the talk from 2 former students of mine saying, box plots with exclamation points. One at the time PhD student and one at the time master's student from here that had gone on to other places to work in the same field, and they literally both texted me right away, box plots, because it was like, I can't believe this is happening. But it was cool because it was useful. That was the one time I've seen it. And I can't remember what the talk was on. Because when you go to a conference, eventually you get conferenced out and you just can't think. The first day is great. Learning so much. It's fun. I'm seeing all my old friends. Then you go drinking all night. And then the conference I go to in Florida, we're very cognizant of the fact that people want to do that at night. So it doesn't start till noon. It's very smart. But the first night, it goes from 7 o'clock at night till like 10:30. But that's okay, yeah. Eventually, after about 3 days, you're going, ugh. Do I have to speak today? Because I can't. No one's paying attention to your talk. That's not true. Some people pay attention. All right. I'm running out of titles, so I just said, and it continues. Okay, so that gives us some ideas. Oh, what I should tell you, the way you the whiskers. Looks so stupid saying that. Whiskers, come here. The whiskers in the box and whisker plot. How do you know how long to make them? There's 2 ways. One of them is just go all the way to the minimum and maximum, which is what I did on that one. The other way is to go. You figure out what the interquartile distance is, which is Q3 minus Q1, so 75th percentile or 3rd quartile minus 1st quartile, or Q1. That gives you what's called the interquartile distance. That's between the 2 ends of the box. And then what you do is you make those whiskers 1.5 interquartile distances long. It wouldn't make any sense with those data because it would actually go below 0. And you can't score fewer than 0 goals in a season. Though many members of the Ottawa Senators are trying. It's a crap. Imagine being a Senators fan must be awful. There's no future, there's nothing. You just sit around going, and your owner's awful, like there's nothing good. Right? You just sit there going, we're screwed. You gotta know Matt Duchesne and what's his name, Stone, are sitting there going, like even Toronto a few years ago, you knew that they were bad, but you thought they're going to get pretty good soon. They got a lot of good young guys. And Montreal this year, it's like they're surprising this year, but they got all these great guys in the pipeline. And they're Ottawa fan going, I don't know what we're going to do. Like, I played 4 games for the Senators this year. 9. And they're just dejected, and their owner's suing another guy. He's suing his former partner for $700 million. What? It's great. I feel bad for Ottawa fans. It's not really. So you can't. So it made no sense to go below 0 at that point. Okay. So we've got the shape. We've dealt with that. Let's look at central tendency, right? So one of the 3 properties necessary to describe distribution: shape, spread, and central tendency. So all that kurtosis stuff, and we just, skewness. Okay, so consider the following data or batch of numbers, bunch of numbers. Here's some numbers, 1, 5, 9, 20, 30. And here's another set of numbers, 11, 12, 13, 14, 15. Those both have the same average. They both have the same mean, 13. They're clearly different batches of numbers, right? But they have exactly the same mean. So in this case, mean isn't giving us useful information to compare the distributions. It's not like the mean isn't useful, but what this is giving us is not useful. What it's giving us is not useful. So on its own, it's not going to be useful. Okay. So they're the same but different, as I'm saying. So there's our 2 batches of numbers again. They're both symmetrical, and they both have the same mean. How are they different? Well, the one at the top is much more spread out, isn't it? The one at the top is much more spread out than the one at the bottom. So, well, let's think about spread then. How could we measure spread outness of a distribution? Well, there's a lot of ways we could do it. The easiest thing is the range, and that's a very crude measure, but it does give us some. It does give us something for those two batches of numbers. But it's really only a start. I'd like something that I could use and I'd feel good comparing numbers, right? So we got 1 to 30 versus 11 to 15. We know that one of them's a lot more spread out. Okay, fine. It doesn't tell us anything about the numbers in the middle, though. It's crude. It's useful, but like I said, if we only have 5 numbers and the mean's 13, so this doesn't tell us a whole lot about the numbers in the middle here compared to the numbers in the middle here. In fact, they could all be exactly the same except for 1 and 30 and 11 and 15. Right? So it's not going to help us a great deal. We could use interquartile distance, which with a small batch of numbers like this isn't going to be horribly useful, but it would be a little bit better. It's still also just a crude measure of spread. Okay. So we need something kind of mean-like. Right? We need something like the average amount that a number deviates from the mean. That would be great. Well, let's do that then. The average amount numbers deviate from the mean. It's obvious to do that. The calculation is not going to be too complicated, so let's do that. So remember, we have 13 as the mean, and we're going to take each number and subtract. So sum of the x's minus x bar over n. So 1 minus 13 plus 5 minus 13 plus 9 minus 13 plus 20 minus 13 plus 30 minus 30 over 5 is, it's 0. Oh, shit. It all seemed so great. It was so grand. We had an idea, and it was destroyed by math. I was acting. It's probably the most acting I've ever done in my life. Pretty good, right? I will not be quitting my day job. When you think about this, it has to do this. The mean is the balancing point, right? So you're going to have as much on one side as the other. So if you're just taking those numbers and subtracting, it has to sum to 0. If it doesn't, literally you made a mistake, or math just changed, and the universe changed, and we should all be very frightened if the universe just changed. Because if the laws of physics and math all change, we're screwed. I can't change the laws of physics, Captain. But Scotty, you did it every week for the last season. I'm pretty excited about the new season of Star Trek Discovery. They're going to run into Captain Pike and Spock now. It's a week away. So it's got to be as much numbers on one side as the other. It's about a mass of numbers, sort of, right? So how do we get rid of negatives? Well, the easiest way is the absolute value. And you remember when you were in, probably grade 7, when you learned about absolute value, and you thought to yourself, I will never, ever, this will never come up in my life. Well, ha! It did. Spoiler alert, it will be completely useless, but it comes up. It'll be useless from our perspective. It's actually a really intuitively pleasing thing with the mean absolute deviation. So we're just taking the absolute value, which, again, now I should never say you learned this in grade 7 and you remember, because now everybody's going to go, I don't remember my hand up and say what's an absolute value, because I look dumb. Absolute value is just the number without the sign, right? Absolute value of x minus x bar over n, so that becomes 12 plus, minus 12, that's 12. So 24 and 34, 9.6. Yay! That's great. And it actually looks sensible, too. So the mean absolute deviation is 9.6 in this case. And this is wonderful. And it's intuitively pleasing because it's telling me, on average, the numbers deviate by almost 10, so between 9 and 10 from 13. That's great. And we can do it for the other one. In fact, that's an easy one to do because it's all ones. So it's 4 divided by 5, right? Because one of them is 13 minus 13, which is 0. So it's 4 divided by 5, which is 0.8. And we know that that other distribution is way less spread out. Wow. That seems wonderful. So I think it's pretty cool. And sometimes, like I said here, things seem cool at the time, but they really aren't. So the mean absolute deviation is a statistical dead end. It's not useful for the kind of stats we want to do. It has uses. It's just not useful in the kind of inferential statistics that we talk about, what are called parametric statistics, which allow us to estimate parameters. It has uses in statistics. In inferential statistics, it has uses in what are called non-parametric statistics. It really does have a use. And it gets trashed a lot by people who write stats books and people who teach statistics. It actually does have a use. It's just not a common one. It's mostly for non-parametric stats. As you can see there, comparing those two sets of data, 9.6 and 0.8 are vastly different. And one that's basically saying one's about 10 times more spread out than the other one. And yeah, that's about right. Except that's the end of what we can say about the distributions with that statistic. So it's not useful for our purposes. It has uses. So it's a dead end for us. So it's just a dead end. It's too bad. The thing is, I really like it because it has intuitive appeal, and it would be, if we talked a lot more about non-parametric stats, which aren't great, actually. All they do, I'll tell you the difference. Parametric statistics allow you to say the populations are different. You estimate correct population parameters. Non-parametric statistics say that batch of numbers is different from that one, which is true and great. And also, I'm not saying anything about the population. And I want to say things about populations. Right? So it's a shame, actually. It really is. But that's life. Right. There's got to be a better way, and obviously there is, or we'd stop, and you all know what it is. The other way to get rid of negatives is squaring numbers. So negative 1 times negative 1 is 1. 2 negatives make a positive. 2 wrongs make a right. No, that's too far. So in that case, we can square the deviations and we have something useful. And that's what we have here. So I squared these. So 144, 64, 16, 49, 289. Square them up, add them up, divide. That was just for me, but I thought it very funny. Divide by 5, we get 112.4. Great. And you all know about standard deviations, right? I remember last time I taught, most times when I taught 2126, I'd talk about this. And then people were writing down all this mean absolute deviation, and then when I'd say it was useless, you'd hear half the class go, oh, well, here I got something for you. It's like, seriously, it's a teaching technique. I'm trying to show you that it's a thing. Oh, did I waste all your precious time? I'm sorry. I'm up here, you sit there, write shit down. I had a student once in 2126, and he was great. Friends with him still, and he's got Asperger's, so he would just say things to people, and he was really good. He was a good student. He's got a master's degree there. And one day when somebody was complaining about the course, he said, "Maybe if you shut up, you wouldn't. you do better." And I looked over and said, dude, that's my job. I don't get to do that. Just stop talking. And then later after class, it's cool, don't do it again. You say what I think. It's a great guy. He was very funny too, because he just, and the whole class, and everybody stopped talking. Oh boy. All right. The issue here, of course, that's a mighty big number, and of course it is because they're squared units, we have to take the square root to get them back to the original size. The original scale, I'm sorry. So we take the square root, and we're in business. So variance always has to be a positive number because it's squared numbers, right? So if you're ever calculating this by hand, which typically you're, well, with a small batch of numbers you might. I know with a small batch of numbers I would. If I had like 10 numbers, if I put it this way, with my honor students, if we're looking at data and they've got like 10 subjects per group, which is 10, I just do it by hand because it's quicker than booting up a computer and putting the data in for me, right? So it's easy to do. You get on a calculator, bang, 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 done. But if you get a negative number, you've made a mistake. It's impossible to get a negative number when you've squared a bunch of numbers. So we take the square root of that, we get 10.6. And that's actually a lot like that 9.8 we had. So the intuitive appeal of mean absolute deviation is great, but we get something that comes up with a similar number that we can use for parametric statistics. So it's perfectly fine. Now there is a problem here, and you guys know this, that the formula I've given you has n on the bottom, right? Sum of the x minus x bar squared over n. The issue here is that we can't divide by n. Well, we can, I just did, there's no law. But regulatory body's going to come after me. But and it does make sense that it should be n, but it's not n. Remember, it's not a mean that we're calculating, so we're not dividing by the number of numbers. We are dividing by, we should be dividing by n minus 1. We want something that's an unbiased estimator of the population standard deviation. Okay? Unbiased estimator. We want it to overestimate as much as it underestimates. It's not going to get it right on very often. What we want to know, on average, over an infinite number of trials, it will overestimate as much as it underestimates. That's what we want to see. And we get that by dividing by n minus 1. So the population parameters, variance and standard deviation, have n on the bottom. And the sample statistics have n minus 1. If they had n, in fact, they would underestimate the population parameters. And we're trying to estimate them accurately. The beautiful thing is we know how much we would estimate or overestimate or underestimate. We can fix it by doing this, okay? So that's what when we know this, you know this. There's s squared and there's s. We're dividing by n minus 1. N minus 1 is the number of degrees of freedom the data have. This is a hard thing to kind of get your head around. But the numbers have freedom to vary. You're thinking, but they're right in front of me. They can't vary. Yes, I know. But if you did an infinite number of times sampling from a population, they have freedom to vary. Okay? So the numbers themselves must sum to a certain number. We have fixed a number when we did the calculation. When we do the calculation with this formula here, we fix this. This is actually, we put that in there. In our case, we have 13, right? So we put that in there. We know we have a certain number of numbers, because that's n. That's another restriction we put on there. So let's say we have, make the math a little easier. Let's say we have 5 numbers. And the mean is going to be, let's make it 10. What must those 5 numbers sum to? To get a mean of 10 with 5 numbers. Come on, somebody. Oh, you have a freaking bone here. What must they sum to? 50. So the sum is 50. We know that. They must. We have told the formula that. Give me a number. Doesn't matter any number. Give me, no, make it too small. Just give me a number. 18. There's one. Give me another one. 27 is a good number. What's another good number? 6 is a fine number. How about 3 as well? So what do we have here? We have 36, 46, 54. Is that correct? Did I do that math right? 36, 46, 54. So these numbers here so far sum to 54. Oh, done. That's sum to 50. The first 4 numbers could be any numbers you wanted. Thank you for picking whole numbers. If I complicated to do decimals in my head, I can do arithmetic in my head really well, but eventually, or I get 2 million for shut up. There you go, you're very impressive. And you can do that as many times as you want. There's a number there that's fixed. We have lost a degree of freedom. And we did that by fixing something. We fixed a number. You don't have degrees of freedom in the population because it's a real thing. It's a characteristic. We don't have to worry about that, but we have to worry about it here. Because we fixed a value, we have lost a degree of freedom. Does that make some sense? Which leads to literally the only statistics joke. Which is, we'll end on the only statistics joke. These 2 unbiased estimators are talking to each other in a bar. One says, how do you like married life? The other one says, it's okay as long as you don't mind losing a degree of freedom. I didn't say it was a funny joke. I said it was a joke. There's that in the statistics is the profession for people who find being an accountant a little too edgy. So, that's it for today. We'll continue talking about this stuff next time. And okay, so last time, or if you're watching the video literally milliseconds ago, we were talking about, because I haven't done the video yet, but it'll all meld together. Anyway, I was talking about sample statistics for the standard deviation and the variance. It's funny because standard deviation is a lot more intuitive, like it's in the same units, but we tend to use variance a lot more. We talk about explaining variance. There's a mathematical reason behind that we don't have to really get into. The standard deviation, though, is one that the nice thing about it is it's in the same units, and like we saw last time, it's kind of like it's got the same feel as the mean absolute deviation, so that's a good thing. Divided by degrees of freedom. Degrees of freedom are just the freedom numbers have to vary. Okay? We've arbitrarily assigned one value. We fixed a value. That's this, the mean. So because we fixed that value, right, we've lost a degree of freedom. Okay? And I went through that little demonstration with you guys just throwing random numbers at me and had to sum to whatever the hell it was. I can't remember. All right? Questions? This is where we were last time. So questions about last time at all? I think we're in a pretty good place. Okay. Now, make sure. Yeah. So, in our case, in fact, when we divide it by n minus 1, we end up with 11.85. This is one of those things, by the way, if your calculator does statistical functions, or if your app on your phone or whatever that's a calculator app with statistical functions, make sure you're using the right variance. You're using the one with n-1 as the denominator, not the one with n. And the strange thing is, like my calculator that I got, my God, my first day of graduate school, so in 1988, which still kind of half works. I don't want to throw it away because it has some sentimental value, as odd as that makes sound. So, strangely enough, it's labeled like this: sigma n-1 and sigma sub n. And in fact, there's no such thing as a sigma. It's actually labeled incorrectly. It should be s and sigma. Because sigma, that's the population parameter for variance, or standard deviation, and sigma squared for variance, has n on the bottom. It doesn't have n-1. So you might see that on your calculator or your calculator app. It's wrong, which is really annoying. No one ever calculates these things by hand. You can do them with a spreadsheet very simply. Typically, you would the function in like Excel or Google Sheets or Numbers is stdev. And you just select the values. So it's really pretty easy. So for the population, as mentioned here, sigma squared equals the sum of x minus mu squared over n, and then the square root of that is for the standard deviation. Notice it's a capital X. The capital X means that it's a parameter. They're numbers from the population. The big N means it's the actual size of the population. And the Greek letters tell you it's a parameter. These are population parameters. Okay, so that's a big difference. Population parameters are characteristics of populations. Okay, they describe a population. So they're numbers that describe a population, describe some characteristic of a population. Said that about 40 times now. Whereas sample statistics are estimates of population parameters, and they're about samples. So statistics are about samples, parameters about populations. This is one of those things that shows up on quizzes. And sometimes it shows up to the point until everyone gets it right. So well into the term. So on Thursday, if it says parameter, just say a number that describes a population. That's good. It's usually unknown, because if it was known, we wouldn't have to do statistics to estimate it, would we? We'd know it already, so why would we do the stats? We know the population parameter. There are cases we know it, right? So if we have something like, if we have a test that is designed to have a certain mean, certain mu, IQ tests have a mean of 100. They're designed that way. So in the population it's 100. And the standard deviation is designed to be 15. The reason why we use IQ tests a lot in statistics examples and early on in you take like an intro stats course is because we actually know the population parameters. We usually don't. Right? Another example might be if we have two populations. Two populations. We think they're two populations, but they're actually one. The difference between those two groups on some variable. What would the population parameter for that difference be? So if we have two groups, but they're drawn from the same population, and we're gonna, it could be any variable, I don't know, height. What would the difference between the two groups in height be for that, the population parameter for that? What do you think?
I don't understand.
Okay, you got two groups of people, and we're going to measure their heights, and we're going to see if they're different. Let's pretend we know they aren't different. Let's pretend we actually know they're from the same population. If we knew that, we wouldn't have to do anything. But let's pretend we knew that. What would we expect the difference between those two populations to be?
Not much.
Is 0. Not much, not anything. Shouldn't be anything, should it? Right? So in that case, we can get the average height difference between two groups that come from the same population should be 0. And we use that to our advantage a lot in statistics. That's something we do all the time. We set up a situation where we can estimate, where we can actually know the parameter theoretically, even though we don't necessarily know if they're two different groups. We don't know, but if we're assuming they're the same, which we do all the time, right? That's always our null hypothesis, right? That there's no effect. The two groups are the same. I'm glad I can remember what I'm that's what I'm sure that most words. I look really stupid. You look fine. I look stupid. I'm Bryce fanboy. No, the interview was good. You were really good in that, by the way, that I saw on YouTube. That was really good. The other guy's not sitting there. He's not a psych student, right? No. Yeah, he's not that. He was fine. I'm kidding. I kid because I love. So we do that all the time, right? We say, let's see these two groups are the same. We start that way. And then we see if the parameter estimate we come up with is different than what we know it would be if they were the same. We always do that. Okay. That's actually the basis of almost all inferential statistics we're going to talk about in the course. We've always all right? You didn't spit anything on your keyboard, did you? When you laughed? Because I'm just going to say it's not my responsibility. There is no off position on the Dave switch, and that just happens. Okay. Questions about that? So these are all parameters. Capital letters, as a rule, and Greek letters, as a rule, mean parameters. Latin letters, as a rule, mean statistics. Okay? Statistics you calculate from a sample. Parameters are numbers that are usually unknown that describe a population. They tend to be estimates. They are estimates of population parameters. But that's all they are. Okay?
Can you say the definition of statistics again?
Statistics are numbers you calculate that describe a sample. The calculation may be very easy, and you can say statistic, and it's just counting the number of observations, right? So that's a really easy one. Okay. Other questions? It's good. This is basic stuff. What I mean by that is I'm laying the groundwork here. So, okay, you're good. All right, so we can move on. How are the variance and the standard deviation affected by extreme scores? Extreme. So, ever since Harold and Kumar, I say that whenever I say the word extreme. Okay, 159, 2030, that has a standard deviation of 11.85. We've calculated that before, right? Okay, let's throw in a new number, and let's make it a big stupid number. Also, in 729. Squared? So, anyway, one of those things when I was a kid, you had to learn all the squares and square roots of all numbers. 25, so you could do arithmetic in your head because they used to teach us things. So, now our new batch of numbers is 159, 20, 30, 729. Okay, our new mean is really big, 132.33. And it's going to be big because it's been added on. We know how to calculate a mean, so we're going to add all these numbers up, now we divide by 6. The new standard deviation, our new variance rather, is 85,555.067. So our new standard deviation is 292.5. Wow. We've added one number. We could probably make a case that that's an outlier of some sort, perhaps. Right. I don't know. But the point is, it seems that the variance and standard deviation are affected by extreme scores. It doesn't seem like it, it's just true. Okay, so that's just by example. So if the mean's affected by extreme scores, and we use the mean to calculate the variance and the standard deviation, it too, though they too, must be affected by extreme scores. Right? And extreme doesn't really have a definition, it just means something way out of the ordinary, I guess. This also makes sense, right? So, can we use this in any way to our advantage? We can look at something called the coefficient of variation. This is mentioned at the end of the chapter. This is by Katz et al. In 1990. That's where the data come from. Okay. So there were two groups. One group studied, I think these were physics problems. If I remember the study properly, I haven't read the textbook in a long time. And their mean score was 69.6. Their standard deviation was 10.6. The group who didn't study, their mean score was 46.6. Well, it makes more sense, right? They're failing. It says something. And their standard deviation is 6.8. One could conclude from looking at these numbers that there's more variation when you study, right? And that's bizarre. Think about it. Like, why should there be more variation when you actually learn the material than there is when you don't learn it? Hey, go ahead, Sean.
Well, the amount you study is not necessarily saying what you're getting out of said time studying. It's not the same what you're studying and how that translates. So what's being tested is not the same.
It could be. I mean, that's a reasonable deduction. I mean, it's certainly conceivable that what you're saying makes some sense, right? That basically, in essence, some questions are just easy and everybody gets them, and some are just, unless you've really studied them, you're never going to get them. So that means there'd be less variation when you study and more when you do study, because there'd be stuff you had to learn and different people have different levels of expertise. It's a convoluted explanation, but it's an explanation, not a bad one. But this does look odd to me. This would surprise me. If I had two classes, right, and I had one class that had a standard deviation here and one class that had a standard deviation here, I'd be concerned. I'd be more concerned if I had one class that had a mean that much lower than the other. Would that be the first thing? I've taught multiple sections of intro before. Once I taught 3 sections of intro. That was all I did. Which was bad because you don't know where you are in each class, and you think, have you made that joke already? Which is, for me, as you probably know, really I'm just here for the laughs. And learn something on the side that's wonderful as a side effect, but really, to me, the main effect is, did you have a good time? Did you enjoy the Dave show? So the thing is, I got so confused, but the nice thing, I do the test, and I look and I go, the average in both of these classes is 57. That's horrible, but at least it's the same. Right? And it was, the first test in intro, and people are coming in, they don't know anything. Remember your first intro class, no matter if it's biology or psychology, you went in and you took any of those tests and you went, oh, university's hard. You have to study everything. My marks dropped 17 points in the first year from high school, which is a little more than most people, right? I did well anyway, but my marks dropped, my average went down by 17 points. So we might conclude there's more variation with study, and as Sean said, there is a sensible way to explain this, but it may be, if we take the coefficient of variation, the CV, which is a calculation not enough people do in situations like this. And all you're doing here is you're taking the standard deviation and dividing by the mean. Look, we fixed the mean. Why not standardize the scores by dividing by what we use to calculate the mean? That's all that is. And suddenly, we look and we see 1.152 and 0.146. Oh, actually, the difference in the variance is simply due to the fact that the mean is bigger. That's all it is. This is one of those cases where not enough people do this when they're doing sort of exploratory data analysis. So it's saying it's simply explained by the fact that this is a bigger number than this. It's not explained by studying makes some people dumber. That's, right? Or some kind of crazy explanation like that. So you can sort of use the idea of knowing about this to your advantage. Oh yeah, right there, standard deviation divided by mean. It's one of these things. I think I've seen people talk about coefficient of variation before in a paper. Usually when there's something like this and they say, we did that, and you can see that it's just due to the mean being different. People, oh, okay. It's not usually something that shows up in a paper or a talk. I should go back, but leave that slide there, but there's an issue that I kind of forgot. We talk about measures of central tendency, and we see the means affected by extreme scores. In a case like, whatever it was, 11, 12, 13, 14, 15, 729, why don't we, instead of using the mean in that case, if we're going to compare two groups, maybe we compare the medians. Right? There are cases when the median is much more sensible comparison. You see this a lot in labor negotiations. They sometimes get nasty and go through the media. When I was at Newfoundland, we went on strike. And the administration was saying, the average salary is whatever it was, $90,000. And I was thinking, well, that's not what I make. And the administration was using the mean, and that's perfectly sensible, that's fine. And the union said, actually, the median salary is about 52. There's some people that have been here 40 years, and they make a lot of money. But what about all the Brodbecks? Well, they didn't say that, because that's weird. Right? Because then people would say, well, then clearly, we shouldn't be paying them anything. But there were a whole bunch of us that were making not very much money, and then some people making a whole lot of money, and it was pulling the average up. So in that case, using the median makes a lot more sense, right? So you hear about when they say look at stats like about the national average income, things like that. Oftentimes the median's used instead of the means, because there are some really wealthy people. Not as much in Canada as there are in the States, right? Which I find funny as well. Right, the whole 1% thing in the States, it's millions and millions of dollars. In Canada, it's below 300,000. Right, so it's not like our median mean household income is that different in Canada. In the States, it's a lot different, more than any other Western country. So the median income makes a lot more sense to use wherever there's larger, say, income disparities. Okay, back to what I was going to talk about here. So there's a couple of other points. We want to learn about populations, not samples. We calculate sample statistics, but we actually don't care about them. Right? Like, we want to do it properly, we care that much, but it's not like we're trying to estimate sample statistics. That's uninteresting. We're trying to talk about the population. We want to estimate population parameters with sample statistics. If we knew the population parameters, we wouldn't have to do the experiment. We could stop. Thing is, we usually don't. That's why we do science. That, and of course, the paycheck. Yeah, we get published, promoted, all that good stuff. We want unbiased estimators of parameters. And you say, Dave, but if we don't know the parameter, the value, how can we know if we're overestimating or overestimating? Math, that's how. So there's a lot of behind-the-scenes mathematics that happens here. All this stuff was developed from first principles using calculus. I'm not going to go into that so much. Like I said, it will come up. But the thing to remember is that we know, or we can know theoretically, how much something under or overestimates, which ends up why we do things like divide by n minus 1. The mean, on the other hand, is an unbiased estimator, x bar, of mu, of the population. S is an unbiased estimator of sigma. Okay? So if we were to take some numbers, this isn't hard. This is the thing people, I think, have the most trouble grasping. And this, first of all, you're going to see some notation here that you should get used to. The E, and then with brackets, parentheses, that means the expected value of. Expected value just means what you would get if you calculated something an infinite number of times. Okay? If you calculated something an infinite number of times, what would you get? What is your expected value? The expected value, first of all, of x is x bar. X is a variable. Okay. So the expected value of of x, if we calculate x, if we sample x an infinite number of times, what should we get? We should get the average. Does that make sense? We expect to get the average over an infinite number of times sampled. So if we calculate, and you can't really calculate something like this, it's just a number. You calculate the average. We would expect over an infinite number of times the expected value of x is x bar. The expected value of k is a constant. K is always a constant. Right? You just kind of, it's like saying, what's the expected value of 4? Well, it's 4. What else could you get but 4 if I asked you what's 4? If I was to ask you what 4 is, remember an infinite number of times you saw 4. It's 4! Right? There are 4 lights. Is that right? Really? Okay. So the expected value of x plus k is x bar plus k. So x is a variable that has all kinds of possible values. The expected value is the mean, x bar. If we add k to all the values of x, we expect now a value of x bar plus k. Think of it this way. Let's make it a little bit concrete. Because some of you are going, x is k, so let's go. I never said there'd be no math. So, let's say it's an intro test, and people do really poorly. As I mentioned, happens. First test, let's say the mean is 52. I would do something about that. And what's the easiest thing to do? Is to add a constant to everybody's score. So let's say what I would expect the mean actually about 60 on the first test in an intro psych class. That's what you expect to get. Over many times, it's not the same as expected value, I should use the word expected, but my experience tells me over all the times I've taught intro psych, the first test will be a mean of 60. If I came up with a mean of 52, that's my fault. There's no way a group of 100 people that we randomly selected 100 people that are kind of slow. It doesn't work that way. It must be that there's something wrong with what I did. So the simplest way, I would what? I'd add 8 to everybody's score. Now my mean's 60. See what's happened here? I've added a constant, and it moved the mean over. That's all that says. The expected value of x plus k equals x bar plus k. So x is a variable. Got a whole lot of scores. We can say it's a distribution of scores. We're going to add k to it. It's going to move the expected value over to x bar plus k. Does that make sense? Okay, the variance of x plus k, it's the same thing, we've done the same thing, is just sigma squared sub x. The variance doesn't change. The variance doesn't change. Think about this. Okay, so here's the scores. This is me. Okay? My arms are the distribution of the scores. My head is mu, or x bar. I add k to all the scores. It doesn't make it any fatter or thinner. Right? They've all just moved over by a k, or I guess we say 8 in this case. So let's say the standard deviation was 10, and the standard deviation is still 10. Sorry, the variance is still 10. And the standard deviation. Does that make sense? I've not made the distribution any fatter or any thinner. I've not spread it out. I've not tightened it up. Now this is actually what the few times that I've moved scores, this is how I move scores. I don't just add a constant to everybody. If I add a constant to everybody, I'm rewarding people who did more poorly more than I'm rewarding people who did well. If you get 90 and now you get 98, your score's gone up 8 out of 90, right? But if I add 8 to someone who got 50, 8 out of 50 is a bigger chunk. I don't do that. I don't reward people doing more poorly than people who do well. I do, in fact, the opposite. So I multiply times a constant. So 52 to 60, 30, 26, 15. I would multiply times times 15 thirteenths. I'm doing the arithmetic proper way. It doesn't matter. But what that will do is it will move the scores over to get the average out of it. So x times k, if I'm going to multiply all the scores times a constant, it moves the scores over and then it becomes x bar times k. That shouldn't surprise anybody, right? Does that make sense to everybody? And when I say that seriously, you have to stop me if it doesn't make sense, and I'll explain it again. Using different words.
Yeah.
Okay, good. Yeah, thank you. Please do that. Because I just have to assume that you understood it. Okay, good. So I've taken all the scores, and I've just multiplied them times a constant.
Can I clear something up before you even go there?
Yeah, please.
Okay, so these 4 things, you're looking at, if you're looking at a set of numbers that aren't where you want them to be, these are 4 different ways.
These are 4 different things that happen. No, they aren't the same thing. They are things that happen when you do different things to distributions. The first 2 are for adding to the distribution, adding a constant. The second 2 are for multiplying.
And it's for the same end?
It could be. I mean, in this case, in the sort of concrete example I'm using, what I'm trying to do is get all my scores to have the same average, an average that I want.
Okay.
But it needn't be. Yeah, okay, so, good question. And Hannah, do you have questions? Does it make sense yet, or are you still?
I want the multiplication thing revisited.
Okay, so, all I'm going to do here is multiply all the scores times some number. So to go from a mean of 52 up to a mean of 60, what do I have to do? I got to multiply times some number, right? That'll get me to 60. So I want my final thing to be 60, and let's see, so it's x bar, which is 52, times x, right? Make sense so far?
But x is k.
I know, I should be k. So I'm so used to doing algebra with x is the unknown. It just,
Yeah, I know.
yeah. So k equals 60 over 52,
Okay.
which I think is 15 thirteenths. If I did the arithmetic in my head.
Long time.
It's 30 26s, 15 thirteenths. It's 15 thirteenths. And whatever that works out to be, 1 point something. Okay. If I do that, I now have a mean, again, of 60 in our concrete example. I've moved all the scores over, but as I said, I've moved the higher scores over more. I'm going to go back here where I have the distribution. The higher scores are multiplied times 15 thirteenths in our case of k. here. These move a bit, but not as much. I'm going to move over a bit because I'm not going to pull this way. I've changed the standard deviation. I've changed the shape of the distribution. When we just add a constant, we've done nothing to the spread outedness of the distribution. When we multiply times a constant, we've done something to it. Let's make this a little easier so I can do arithmetic in my head a lot easier because it's hard for me to. So let's say we have now a variance, in our case of, I don't know, 81. I'm just picking a number. And we're going to multiply times a constant that is 4. Okay? I'm going to say k is 4. So now our new variance isn't going to be just 81 as it was before. It's going to be 81 times, we multiply times 4, 4 squared, or 16. Which is carrying ones and such in my head. 81 times 16. So our new variance would be 1,296. So what's our new standard deviation? Because it doesn't say it there. Don't do the arithmetic. Just tell me what it is. Just divide it. It is actually as obvious as some of you are thinking. Take the square root of s squared times k squared, so it's s times k. So now our new variance, our new standard deviation is going to be, let's see, 81, that's going to be 9, and that's 4. So it's 6. And I will bet you proper money that 36 squared is the score from before. One of the ways, if you're ever doing this, if you're ever required to do this for some reason to test that you've done it properly, is just say, well, I'm just going to square that and see if I get the same score for variances doing it this way. Now, think about this. One of the questions on the homework assignment is actually doing this. Are the heights in centimeters or inches? They're in centimeters. And we're turning them into inches. So we're dividing by 2.54, right? Yeah. Division is just multiplying times 1 over a constant. Isn't it? Right? So if I'm going to divide by, if I divide by 2, all I'm doing is multiplying times a half.
Yeah.
Right? So what's going to happen if we're dividing is the variance is going to be x bar divided by k, and the variance, the expected value of x times k, so the mean, and the variance is going to be s squared over k squared. Right? Because division is just multiplying times 1 over a constant. Right? Just like, what about subtraction? Subtraction is just adding a negative number. So, and it's interesting because one of the questions on the assignment says, what happens to the shape of the distribution? And it's got to change because we're multiplying times, well, we're dividing by a number. It's going to do certain things to smaller numbers differently than it does to bigger numbers. So it makes, the variance is different, the standard deviation is different, the mean is different, the distribution is different, it's going to look different. But does that matter? No, it really doesn't, does it? Because they're still measures of height. One's in centimeters, one's in inches. But they're still measures of height. So while the shape of the distribution seems to change, perhaps, because you multiply times a constant, it doesn't mean that the distribution itself, the basis of it, has changed at all, because it's still height you're measuring, and you're still just using 2 different measures of height. Right? It would be like, would you say, for example, that if you were to compare incomes in the UK and incomes in Canada, and the raw number you get in the UK is much smaller, because their money's different, they use pounds. Right? So it's like, oh, wow, they hardly make anything over there. Not true. There's an exchange rate, you know, like this. We've all gone to the States, shopped, and such. So we know about that. You shopped online and you went, oh, gee, that t-shirt's only $16. Oh, it's $23 actually. Right? It's still the same t-shirt, you're paying the same amount of money, just a numbers difference. So even if you have done this to a distribution, it doesn't necessarily mean anything. Okay? Do you have any questions about this before I move on to something else? Or anything else we've talked about in the first class? 2/3. Sure. Yes, go
I
ahead.
have a
Sorry.
question. I'm not sure how to word it.
You're also apparently not sure to speak.
Yeah, that's
Sorry,
right.
question.
I
I will walk all of you mercilessly. Just keep that in mind. Okay.
Okay, so like if you're doing things like the median,
Yeah.
if you have an even number of numbers, do you take the halfway of the
Yeah.
two numbers that are in the middle?
That's exactly what you do.
Okay.
Yeah, that's exactly what you do. So, and that's a good practical question. It's what you're doing is technically doing something called linear interpolation, but when it's just two numbers, it's just a middle. Yeah. So if it's you got 10 numbers on one side, 10 numbers on the other, and the 10th number is 7, and the 11th number is 9, the median's 8.
Yeah.
Yeah. Please.
So when you're talking about the coefficient of variation,
Yes.
you said sometimes people do it, sometimes people don't do it.
Yeah.
When do I know to do it?
For exploratory data analysis, if I was comparing two groups, I would do that right away. It's just something I would do because I just look at it and go, I wonder why these variances are different. If your variances are different. By the way, there's a rule of thumb about variances being different.
Okay.
Is one more than 4 times bigger than the other?
Okay.
So in other words, is one twice the size of the other? That example there, it was almost twice the size. So that's a case where you go, yeah, this is something.
Okay.
And that's just a rule of thumb. It actually, the math behind why that's a rule of thumb is that people have done millions and millions and millions of simulations and found out that most things hold up just fine in statistics as long as one variance isn't 4 times bigger than another.
Okay.
So that for practical purposes, as long as a variance isn't 4 times bigger or a standard deviation twice the size in two groups, I don't care. And there's ways to fix that, by the way. In fact, you do what's called the transformation. That's why I'm introducing it now. We'll talk about it in about a month. But there are things you can do, and they're mathematically exceedingly sound. It's basically changing the scale, right? So that's all we're doing here is we're just changing the scale.
Right.
It sounds like cheating, right? But it's not. Please go ahead.
So when you're looking at, I apologize to all of you guys
No.
in this room about these. Like,
No, you probably all have the same questions as she's asking.
When you're looking at a set of data,
Yes.
okay, is there like a very specific list of things you go through that you do in the same order every single time?
Okay. What I do
Yes.
is different than what everybody else has their own idiosyncratic thing. Too many people don't do it at all. I will tell you that right now.
Okay.
But the first thing I do is I literally, it depends. The stuff that I do, it depends. The stuff I'm doing right now, there's going to be a lot of that. Typically, the stuff I do doesn't have a whole lot of numbers, but what I'll do is I'll just look at them. I have been looking at numbers a lot enough in my career that I can look and go, that's weird. But that's the first thing I do. Then I just get means. It's from different groups.
Yeah.
Okay, I'll just get means and look at them, and I look at standard deviations and means together.
Okay.
If it's a small enough number, I actually do the calculations myself. I don't let a computer do it, and then I do it with a computer to make sure that I haven't put things in wrong. Seriously, because it doesn't take me long to do that.
Mm-hmm.
And again, I've been dealing with batches of numbers enough in my career that I can look at a batch of 20 numbers and tell you what the standard deviation is roughly. roughly, like not like within a couple of points, and I can tell you the mean because I've just done this enough. It's not some special skill. You do. It's like you can probably drive a car. I can't. So that's what things. Then I graphs. I love making graphs. Again, and I don't care about the axes so much because it's my data, so I know what to expect. So I'll just usually tell Excel or whatever, or Google Sheets, give me some graphs. I'll just use the histogram function, and it just makes me some graphs. And that's where I start finding weird things, if there's anything weird.
And then you'll start looking at this stuff.
Oh yeah, that's then we start going further into
Okay.
stuff. Yeah.
Okay.
But I mean, at first, I'm just looking at numbers, calculating means, standard deviations. But that's my approach. It's my sort of. As my wife, as the artist, would say, that's my process. Everybody does it differently, right? Most people they'll do, if they got a small enough data set, will just literally look at the numbers as their first thing. You have to have a feel for it. Like you have to know that when you find something, you gotta look at it. Why is that a double-digit number? These are all single-digit numbers. That's weird, right? The stuff I'm doing now, starting this week probably. You know, we have these birds flying to different feeders, and if one day suddenly we have hundreds and hundreds of visits, and every other day we have like 9, something weird's going on, right? I would go to the people that are actually collecting the data. It's not a spreadsheet, and I'd say, what happened here? And they said, well, it's, I don't know, it was really nice that day. And that could be the difference, right? Like, let's say we were collecting data on this bird feeder experiment and we were doing it on last Monday and Tuesday. There wouldn't have been a lot of activity because the weather was horrible. But also, maybe there would be, but maybe our video cameras couldn't detect it because the weather was horrible. Right? I have a friend who does work, again, in a field like that, but has birds are all tagged. And then she finds out some days that the birds just, oh, I don't get it. The thing says no birds came, but this other thing says that there were like 800 trials ran. Something's different. There's a discrepancy here. Something's wrong. Right? That's happened with this, my friend Emily's work. To the point where she had to stop doing it that way. Which is a shame. Other questions? These are good questions. Good practical questions like that. Okay, to stop this part, so we do